Hey everyone. So today we begin Unit 3, which is on optimization and curve sketching. Okay. And so our first lesson is on increasing and decreasing functions. We'll also take a look at Fermat's theorem by the end of it. Okay. There's a lot of ground to cover, as there often is in the first lesson of any unit, but it's not complicated ground. I think it'll be familiar ground, okay? We're using it kind of as a stepping stone as we go. Okay, so consider the following function, okay? And you have this in your notes. With respect to the derivatives, the domain of this function is going to split into 3 levels. Now, what I might like for you to do first is just in your own book, take a little sketch of what the derivative would look like, okay? We've done questions like that before. You know that when the position function changes direction, right there, the derivative will equal 0. So I've got a 0 there, and I got a 0 about there. Then you know that the derivative will be negative when the function is decreasing, and it will be positive when the function is increasing. So I'm going to be looking at something like this, right? That'll be the general shape of the derivative, okay? Now, that's not the actual equation. That's just a quick sketch to think about the general shape, okay? But essentially what I want you to think about is we have 3 different domain sections based on whether the derivative is positive or negative, okay? And so we're just going to have a quick conversation around each of those 3 sections. So this first section, the one on the far left, would be from negative infinity all the way up to -5/2. And for that guy, all of the tangent lines of so the derivative would be greater than 0, and all of the tangent lines would have positive slopes, okay? And the actual position function is increasing. The y values are getting larger as we go. That next section would actually be from that -5/2 all the way over to here. Now you have it labeled in your book, but it's at 3/4. If you can't read my grids there. So that would be from -5/2 to 3/4. Now what's happening here is all the tangent lines are negative slopes because the derivative, f derivative of x, is less than 0, okay? And on the actual position function, we see that the function is decreasing again. The y values, as we go along the x for that section, the y values are getting smaller and smaller and smaller, okay? And then the last section would be from 3/4 to infinity. We're back to the derivative being greater than 0, so the derivative is positive. And then all the tangent lines will have positive slopes, and the function will be increasing, okay? So this shouldn't be a, what's the word? This shouldn't be like a huge, profound statement when I say when the position function or the original function is increasing, the derivative ends up being greater than 0. And when the original function is decreasing, the derivative ends up being less than 0. What happens at those turning points? So at -5/2 and at 3/4, well, you guys know this already too. At -5/2, the derivative is equal to 0, right? We get a tangent line that it has a slope of 0. It's a horizontal line there. So the tangent line is horizontal. The function is neither increasing nor decreasing, and that's happening at -5/2 and at 3/4. And again, we already really knew that, right? Where we talked about that with position and velocity, that where the velocity was 0, that's where we changed direction. Okay. Okay, so if the derivative is less than 0, the original function f of x is decreasing on the given interval. If the derivative is greater than 0, the original function is increasing. And if the derivative is 0, f of x is neither increasing nor decreasing. That's that moment in time where we're changing direction. Okay, so next quick little conversation to have is around max and min points. And again, part of this is just you getting used to some wording, okay? We're gonna talk about absolute maxes and relative or local maxes. Absolute maxes mean this graph will never go higher than this point. Whereas a local max refers to, hey, there's a change of direction. There's a high point in the graph, but it's not the overall high point, okay? So even before we start having the conversation with how to talk, looking at this graph, I'm just going to hide myself for a sec so you can see the full graph, but looking at this graph, I would want you to be very comfortable to say, hey, that right there is going to be an absolute max, but this right here still kind of operates as a max. It's just not the absolute max. So we call that a local max or a relative max. Okay. Likewise, here we would have a local min, but the absolute min would be here because that's the absolute lowest point on the graph. Okay. Okay, I'm going to bring myself back. I hope you didn't miss me too much. Okay. So absolute max and min values. The function f has an absolute maximum value at x equals, well, read it off your graph, it would be x equals 10. Okay, and then the absolute maximum value, well, that's just the y value, so that would be 8. We have an absolute minimum at x equals 2. That's the absolute lowest point of this graph. And the absolute minimum value, so that's the y value there, would be 0. Okay? All right, so in general, a function f has an absolute maximum at c if f of c is greater than or equal to f of x for all values of x in the domain of f. Now, this little symbol, I don't know if you've seen that before or not, but it just means for all values, okay? Okay, the number f of c is called the absolute maximum value of f. So whatever f of c is, that's the maximum value, okay? So we say we have a max at c, whatever that c point is, and then the maximum value is whatever f of c is. Okay, a function f has an absolute minimum at c if f of c is less than f of x for all x values in the domain of f. And then the number f of c would be called the absolute minimum value. Okay? Nothing too strenuous there, just a little bit of wording that I want you to get kind of comfortable with. Okay, the extreme values of f are the absolute maximum or absolute minimum values. So if you are asked to calculate the extreme values, that's all they're asking you to do. Okay? All right, so now we're going to take a look at local or relative max or mins. The function f has a local maximum at 4, right there, and 10, right there. Now, we already talked about 10, right? But absolute maximums are still local maximums. They're still essentially a local max or a local min is any sort of turning point that you see in the graph. Okay, so then the local maximum values of f would be respectively 5 and 8. Okay, so we're just looking for where we see those changes of direction. Okay, and then the function has a local minimum at 3. Now notice I didn't state 2 values for the local minimum, where I stated 2 values for the local maximum. The definition of a local max or min is I have to change direction. I have to be on either side of a hump, essentially. Okay, so this absolute minimum down here did not involve a change of direction, and that's why I didn't call it a local minimum as well. Okay, had this point here looped around, then I would have called it a local minimum. But both my maximums did loop back down, and that's why they were both also called local maximums. Okay, so then the local minimum value is 3. So in general, a function f has a local relative maximum at c if f of c is greater than f of x when x is close to c on both sides of c. So f of c has to be larger than f of x over here and f of x over here, essentially. Okay, And then again, the number f of c, whatever that value is called the local or relative maximum of f. A function f has a local or relative minimum at c if f of c is less than f of x for values where an x is close to f of c, or sorry, when x is close to c, but on both sides of c. Okay, and then the number f of c is called the local or relative minimum of f. Again, like we did lots of this in 30-1, just perhaps we didn't use the exact lingo that we're using, but it's very, very similar to what we've already covered in life. Okay, so for each function, determine the absolute and local maximum and minimum values and the values of x where they occur. Okay, so I'm just going to hide myself in case you're looking at this without a workbook. That is the graph that we're looking at. You have it in your workbook though. Okay, so first statement, the function f does not have a maximum. It does not have an absolute maximum. Okay, it does have a local maximum. We'll talk about that one in a minute, but it does not have an absolute maximum because you see arrows on the top of this. This is going to go up forever to infinity. So there is no absolute top to it. The function f has an absolute minimum at x equals -3, and the absolute minimum value would be -15. Okay. All right. The function f has a local maximum. Well, we see that local maximum right here. So that would be at x equals 1, and the value for that would be 10. And then I also have a local minimum at 2 spots. Remember, I need to see a minimum where I have on either side, I'm changing direction. So I do have a local minimum here, and I do have a local minimum here. Okay, so that would be at -3 and at 3. And then the values would be -15 and 5, respectively. Okay. Nothing really too strenuous yet. It's just a matter of getting comfortable with the wording and finding these spots on the graph. In a minute, we're going to do this, figure out how to do this algebraically, okay? Okay, let's just switch functions for a sec. We're going to go to g of x. The function g has an absolute maximum at, well, that would be right here. That graph is never going to go higher than that point, so that's at x equals -1, and the value would be 6. And then I have an absolute minimum. Well, remember, I don't need to change direction for an absolute. The absolute minimum is the lowest point. That would be this guy right here, so that would be at x equals -4. And then the value for that would be -4. It's actually at -4 on the y as well. Okay. And then we have a local maximum. Well, I've got a local maximum here and here. Okay, in both spots, I changed direction. So I have a local maximum at -2 and at 4. Oh, sorry, -1 and at 4. I wasn't reading my graph properly. -1 and 4. And then the maximum values would be 6 and 3 there. Okay. The function g has a local minimum. Remember, I can't use this guy that I did originally for my absolute minimum. I can't use him right now for the local because I'm not changing direction. I don't have, it's not higher on both sides of that point. But I do have a local minimum right here. Okay, so that'd be at x equals 1, and then the value of the local minimum would be 2. Whoops, sorry, I thought I had put my mouse back on. There we go. Okay. Okay, so if we do not know what the graph of a function looks like, how could we find the local maximum and minimum values? Okay, so we're going to just do a little thought-provoking couple questions here. Take a look at this graph. For what value or values of x would f have a local maximum? Well, I would see a local maximum at a, at b, and at e, right? So A, B, and AC. I don't know why I said B. I literally, if you watched my video, did this and then called it B. Sorry, A, C, and E. here, here, and here, okay? Okay. What is true of the derivative at these values? So if I was to calculate the derivative, think about that line, tangent line that you see there, okay? For A and for C, I would want you very confident to say the derivative is 0 there. Now, we might get a little confused with E. What I need you to see here, there's a problem with this guy, right? Because there's a kink. It's not like A and C are. But we've already talked about this in other contexts. You would want to tell me there that the derivative doesn't exist, right? Because I can draw multiple tangent lines just like I did on the graph right there, okay? So either the derivative could be 0, like is the case for A and C, or the derivative doesn't exist, like is the case for E. Okay, so the derivatives equal 0 at A and C, and the derivative does not exist at E. Okay, and most of you are already piecing this together thinking, oh, okay, so if the derivative ever equals 0 or doesn't exist, I'm going to find a possible spot where I change direction, right? That's what you're thinking right now, because you guys are all super, super smart. And you're absolutely right. That essentially is Fermat's theorem, but I haven't got there yet. We're going to go just a little slower. Okay. For what values of x does f have a local minimum? Well, now I'd want you to say, hey, I have a local minimum at B, and I have a local minimum at D. I can't call this a local minimum because I haven't changed direction. Okay. So we're just going to stick with B and D. And then what's happening as far as the derivative goes? Well, at B, again, I would have a derivative of 0. And at D, I would have a derivative that doesn't exist. Okay. Again, because of those multiple tangent lines that I can do there, because there's a kink in that graph. So the derivative of B is 0, and the derivative of at D, sorry, I should have said at D, does not exist. Okay. Okay, so that leads us to Fermat's theorem. If the function f has a local max or a local min, so if we're trying to find the local max and local mins, and like big picture item here, unit 3 is called optimization and curve sketching. The whole purpose of this is we want to be able to draw accurate graphs without our graphing calculator. Well, this is actually how we figure out where those maximum and minimum points are. Okay, this is the theorem that's going to help us. Instead of just like at the very beginning of this lesson, I just gave you a rough, this is something like what the derivative should look like. So we had kind of an idea, but now we're going to actually be able to figure out exactly those points. And then you just have to connect the dots to get the most accurate picture. So if the function f has a local maximum or local minimum at C, then either the derivative of C is 0 or the derivative at C doesn't exist. Okay, in order to have a maximum or a local max or min point, you must either be in a situation where the derivative is 0 or the derivative does not exist. Now, just note the converse of Fermat's theorem is not necessarily true. If you haven't done lots of proofs in your life, the converse would be the opposite statement. For example, f of x equals x cubed. The derivative of that would be 3x squared. And if we took a look at the derivative of x equaling 0, that would happen at x equals 0. But f of x does not have a local maximum or minimum point there. Okay, so what we're saying is just because, so Fermat's theorem, let me put it this way. Fermat's theorem is saying if we have a local max or minimum, then the derivative will equal 0 or the derivative doesn't exist. What it is not saying is if the derivative equals 0 or doesn't exist, we will always have a local max or min. Okay, and so the example I gave you is this f of x equals x cubed. At f of x equals 0, the derivative does actually equal 0, but you know the equation x cubed looks like this, right? That is not a max or a min point, okay? That is a point, though, that we're going to eventually want to talk about, but we'll get there in a little while. Okay. Oh, sorry. Okay, so this deals with something called critical numbers then. A critical number of a function is a number c in the domain of f such that the derivative of f at c will equal 0 or the derivative of f at c does not exist. Okay, so essentially all the numbers that we use for Fermat's theorem, they are called critical numbers. So the very first thing we need to do is find the critical numbers. And the critical numbers, again, are where the derivative equals 0 or the derivative doesn't exist. Those are what we are terming the critical numbers, okay? So Fermat's theorem says that if the function f has a local maximum, local min, it will occur at a critical number, okay? It will occur at a critical number. Okay, so determine the critical numbers of each function. Well, we just said it's when the derivative equals 0 or the derivative doesn't exist. So the first thing we need to do is find the derivative. So I've given you f of x. You write down the derivative of f of x, and you can do that relatively quickly at this stage of the game. It'll be 3x squared plus 12x plus 9. Okay, and now I have to look at where would this graph equal 0 or where will it not exist? Well, this is a polynomial function, so there is nowhere where it won't exist, right? The non-existent ones are where we're going to get into like radical graphs or rational graphs or something like that, okay? But for a polynomial, everything exists along the domain, so nothing doesn't exist. But we do want to see where it equals 0. So we'll set the derivative equal to 0. Just a quick factoring question. You could divide everything by 3 and then factor. You're looking at x plus 1 and x plus 3. So your critical numbers are at x equals -1 and -3, okay? Now, this question just said, determine the critical numbers, so we're done. In a minute, we're gonna take this a little further and see what we do with those critical numbers. But right now, we've answered the question, okay? Okay, what if we looked at f of x equals the absolute value of x? Well, we could look at this from two different standpoints. First of all, in your mind's eye right now, I would want you very comfortable to say, hey, the absolute value of x looks like this. And at this stage of the game, you should be able to say that that's really two straight lines that have been put together, and that's a kink in the graph where the derivative on the left doesn't equal the derivative on the right. So the derivative doesn't exist right here. Here's an example where the derivative doesn't exist, okay? So graphically, we could just say there's a corner at x equals 0, and so the derivative doesn't exist at x equals 0, so the critical number is at x equals 0. Okay, so now if we look at that algebraically, we want to split that into piecewise function, right? We know that on the left, we're looking at the negative version, the version that would have a negative slope, and on the right, we're looking at the positive version, the version that would have the positive slope. So writing that in piecewise function, we can say that y equals -x when x is less than 0, and y equals x when x is greater than 0. Okay, well, let's take that function and let's write the derivative in piecewise function. Well, the derivative would be -1 then, right? The derivative of -x is -1. So I'm looking at -1 when x is less than 0, and I'm looking at 1 when x is greater than 0. So that is enough information to say, hey, the derivative of y at 0 doesn't exist because the derivative on the left doesn't equal the derivative on the right, okay? Okay, so next question is f of x is root of x. Now, remember, critical numbers exist where the derivative is 0 or the derivative doesn't exist. I know that with the root of x, I have an endpoint at 0, right? The graph only starts at 0 and then starts heading its curve. So I have a endpoint at 0, which means I have a critical number at 0, okay? Okay, determine the local maximum and minimum values of f of x equals x cubed plus 6x squared plus 9x plus 2. Then sketch the graph of y equals f of x. Okay, so to do this, I essentially need to find my critical numbers, and then I need to test on either side of those critical numbers to see whether my function was increasing or decreasing. If I go from a increasing to a decreasing moment, then I know I just found a local maximum. If I go from a decreasing to an increasing moment, then I know I just found a local minimum. Okay, so the first thing we're going to do is find the derivative. So that's 3x squared plus 12x plus 9. Now I want to find those critical numbers. So I set it equal to 0. We've already done this particular question, so I went straight to the answer. This was one of the previous questions we had looked at. So 0 equals x plus 3 times x plus 1. So I know I've got x equals -3 and -1. Those are going to be my critical numbers that I need to test. So I'm going to plot those on a number line, and I'm actually going to find a friendly number over here. So over here means I'm going to be less than -3. So some friendly number less than -3, maybe -5 is a nice one to work with. Doesn't really matter as long as it's less than -3. Some friendly number in between -3 and 0, and some friendly number above -1. I get -24, so that means I'm positive on this side. If I was to plug in -2 for the middle section, I get -3, so I know I'm negative here. And then I'll plug in 0 and I get out 9, so I know I'm positive there. So I end up being positive on this side, negative on this side, and positive on this side. So at -3, I'm switching from increasing to decreasing. So at -3, I have found a local maximum. At -1, I'm switching from decreasing to increasing, so I know I have found a local minimum. Okay, so I'm increasing from -infinity to -3 in union with -1 to infinity, and I'm decreasing from -3 to -1. Okay, now I need to actually figure out those maximum and minimum points. So I plug in f of -3. Now remember, that's now back to the original. I'm trying to figure out the points on the original equation. So I plug in f of -3, and that equals 2. I plug in f of -1, and that equals -2. And so I have a local minimum, of -2 at x equals -1, and I have a local maximum of 2 at x equals -3. So I can now plot those, -3, 2, and -1, -2, and then I know I'm increasing, and then I'm decreasing, and then I'm increasing. So suddenly I'm able to draw a much more accurate graph, okay? At the very beginning of this lesson, I gave you a quick sketch of what the derivative looked like, and we were just focused on whether I was increasing or decreasing. Now I can physically say, no, I'm increasing right to this point, and I'm decreasing right to this point, okay? All right, now we want to figure out the absolute maximum and minimum values. I've done a little bit of this already in my previous talk, but we're also going to change the interval. We're not going to have the interval being x to the number of the reals. Now we're going to take a look at it from -5 to 0, okay? So I already know my critical numbers. I already know that one of them is a local max and one of them is a local min. But now I also have to figure out where I am at my intervals. The intervals won't create a local max or a local min, but they may create an absolute max or an absolute min, okay? So this is stuff I already knew. My critical numbers were at -3 and -1, and I already knew that that was the point -3, 2 and -1, -2. I'm now going to figure out f of -5 and f of 0. So f of -5 is -18, and f of 0 was 2. So I have an absolute minimum of -18 at x equals -5. Because when I looked at all of these guys now, I've got y values of -18, of 2, and of -2. -18 is my absolute lowest point. So I know that that's my absolute minimum, okay? Then I have an absolute maximum, actually in two different places because they're both 2. So I have an absolute maximum of 2, and that will occur at x equals -3 and at x equals 0. Okay, so that's my absolute max and mins. So I just look at all my critical points as well as my endpoints, and I decide, okay, which is the highest and which is the lowest. Okay. All right. Procedure for finding the absolute maximum and minimum values of a continuous function on a closed interval. So say a to b. Find the values of f at the critical numbers of f in a to b. Find the values of f at the endpoints. So evaluate, then figure out what f of a and what f of b is essentially. So the absolute max or min must occur at either a local max or min. So either at a critical number or a endpoint. That's why we're doing that. So essentially we're finding all the y values of our critical numbers, all the y values of our endpoints, and then we're taking the highest and we're taking the lowest. Okay. Okay, so determine the local and absolute mins of f of x equals x to the 2 over 3 times 5 plus x on the interval -5 to 1. Okay, so for critical numbers, I want to take a look at the derivative, and I want to set the derivative either equal to 0 or non-existent. Okay, so to take the derivative of this, we want to do it as quick and as easy as possible because the question isn't about taking the derivative, right? We're using the derivative to get to our next section. So what I'm actually going to do, instead of looking at this as the product rule, I'm actually going to do this multiplication right away, and then I can take the derivative of the two different terms. Okay, so that's going to be 5x to the 2 over 3 plus x to the 5 over 3, and now I'll take the derivative of that. Okay, so 2 over 3 comes to the front, so that'll be 10 over 3, x to the -1 over 3. 5 over 3 comes to the front, and that'll be x to the 2 over 3. Okay. Now I want to clean this up, so I want to factor out the x to the -1 over 3. I can also factor out the 5 over 3. So I divided both sides by 5 over 3. And that's going to leave me with 2 plus x in there. Okay, that way I can go 5 times 2 plus x over 3 cubed root of x, or x to the 1 over 3. Okay, so I'm just going to write this as a nice one fraction. Okay, so there's my derivative. Now, if you had wanted to do the product rule for that, you would have got the same answer. It doesn't matter. Okay, so I'm looking for when is the derivative 0 or when is the derivative non-existent? Well, I know the derivative is non-existent because of this. Sorry, I'm just trying to get my ink back on. This guy down here, right? X can't be 0 because if x was 0, I'd end up with a 0 on the bottom. So it doesn't exist at x equals 0. So that's a critical number. And then I know that I'll get 0 when x is -2. Okay, so I have two critical numbers here, one at -2 and one at 0. The -2 one because it creates the derivative being 0, and the x equals 0 one because it creates the derivative not being existent. Okay, so now I'm going to test my critical numbers. I know my critical numbers were -2 and 0. I plot those on a number line. Okay, so I want to think of something to the left, think of something in between, and think of something to the right. And then I want to plug those numbers back into my derivative equation to see if my derivative is positive or negative. Because remember, if my derivative is negative, I'm decreasing, and if the original function is decreasing, and if my derivative is positive, the original function is increasing. Okay, so when I do that, I get positive left of -2. I'm negative between -2 and 0, and I'm positive after 0. So this function will be increasing from -infinity to -2 in union with 0 to infinity. And then I'll be decreasing from -2 to 0. Okay. Now I want to get the endpoints and the y values. Okay, so I need the y value that goes with -2. I need the y value that goes with 0. I need the y value that goes with -5. And I need the y value that goes with 1. Okay. I also know before I do that, just to keep this conversation going, if I'm going from increasing to decreasing, that's going to be a maximum there, right? And if I go from decreasing to increasing, that'll be a minimum there. Okay. All right, so f of -2 is 4.8. F of 0 is 0. I'm just finding the y values for those critical numbers. Now I find the y values for -5 and 1. F of -5 is 0, and f of 1 is 6. So as far as my absolute max or mins go, they must be off of this list. Absolute max or mins have to occur at either critical numbers or endpoints. Okay, so I can see my highest is 6, so I know I have an absolute max of 6 when x is 1, and I have an absolute min of 0 when x is either 0 or -5. Now, as far as local maxes go, I know I have a local max rate here because I was going from increasing to decreasing. Remember that the endpoints can't be local max or mins because I need to have something on either side of them, okay? And so this will be a local max and this will be a local min, okay? So now I need to say all those in statements. So I have a local max at x equals -2. Actually, we'll say a local max of 4.8 at x equals -2, a local min of 0 at x equals 0, an absolute max of 6 at x equals 1, and an absolute min of 0 at x equals 0 and -5, okay? I didn't in my notes here say the absolute min was in both places, but you can say in both places there. Okay. Awesome. All right, so that's it for us. You can try out your homework and see me if you have any questions. Okay, I hope this feels okay. We will talk soon.